Hello and welcome to our first challenge. In this challenge, assume that you are a data scientist or a data mining specialist. Let's say you work for an auto insurance company or data-related consultation company. Your task is to detect if a customer's car was in a crash before or not. This is a great exercise for experiencing how data science works. By completing this task, you will be able to perform basic data exploration and preprocessing. You'll be able to apply classification techniques, and you'll be also able to evaluate the performance of the classification models. All right, this is our data set and we're going to explore it now. So knowing your data as a data scientist is very important, because there is no way you treat the data as black box. So a data scientist has to understand the data in and out in order to do successful analysis. So this is an example of a data set for the same problem we just mentioned. So this data is related to, again, to a car and a customer's information and whether this car was in accident or not. So look at it. There are a few things we have to note here before we start the analysis. And the first is, the rows here, we call them instance. Or in some cases, they call them examples. So the instance is independent examples of the concept. There is another important thing here we have to note, which is the attributes or the descriptive features, or simply they call them features. The features measuring the aspect of the instance. For example, in our first case here, we have an idea of a person, his age, right? His income. In this case, how much is the value of his home or her home, married or not, whether it's a male or female, the profession, the occupation, the travel time per day, the average travel time, the car use, whether it's private or commercial, the car value, how much it is, type, a minivan or a van or a sport car, whether there is an old claim and the amount of the old claim, how old is the car, and then we have important column here which represent the class or the category. This is the kind of thing that can be learned. So in this case, 1 indicating that the car was actually in a crash before, given this attribute. So 0 if it's not. So for example, here, this case was in accident before. Now, the purpose here is to use the data we have in order to develop a model. In this case, since we have a class, we can develop a classification model. Of course, we're going to learn the details of doing this. But the purpose here is to create a classification model. Why? Because I can use this model to help me detect the class of future examples or instances. So once you build a learning system here, when a new customer can come and apply, then straight away you can know this particular case was in accident before or not. This is actually taking us to a very important concept in machine learning. We call it supervised learning and unsupervised learning. And this is a case of supervised learning. Why? Because we have a class or a label. So, since we have a label, then even when we develop a model, we start to find out some patterns could be related to the outcome. And also, this class will help us in order to determine or calculate the accuracy of the model. Meaning, if I have, let's say, for example, this part as a testing examples, I already know the label. I just want to know whether my model will detect it correctly or not. And obviously, in this case, I can calculate how accurate my model is. Well, after we understood the data very well, the next step is to perform our pre-processing. And the purpose of the pre-processing is to clean the data, make it ready for the mining step, or to be ready for extracting more valuable patterns from the data. We have seen a lot of work. People just pick pre-processing techniques and run them in all dataset regardless. And this is not the right thing to do. By understanding your data, you know what kind of pre-processing is needed for this data. For example, if you have few attributes, it's not necessary sometimes to perform, for example, attribute selection. If you have big size of the data with several attributes and you would like to reduce the computational complexity, that is possible. Let's look at our data and let's pause for a second here. Can you see something in the data need to be at least corrected before we go to the next step? All right, let's have a look. All right, how about missing values? I'm sure each one of you noticed that. We have some missing entries here. For example, in this case, here and here. Missing entries or missing values is very important to deal with to improve the accuracy of the training model in most of the cases. All right, what else can you see in this data set? There are some redundancy. And if you see here, the first and second examples or instance are actually identical. So, in terms of the accuracy of the model, the redundancy won't help the model to be more accurate. But it's rather you're adding computational complexity to your training model. Deleting redundancy is very important. All right, what else? How about some entries which are not correct or do not make any sense? For example, if you look here, the car you use, usually we have it as commercial or private. But here, private is spelled wrongly. And for any learning system, we'll understand this is another variable within the same column here. So the column here will have three variables, private or private with a wrong spelling or commercial. And of course, that's not what we want. This entry here should be private, the same. Another thing here, under the gender column, most of the column, as you can see, is either male or female, M or F. Somebody put female here, again will be considered as a third variable, which is not correct in this case. So, this needs to be corrected as well. Here, under age, it seems like the 0 is just added, as a typo. There's no person his age will be 540 years old, right? So the 0 has to be removed. Maybe. But we understand there is a mistake, clear mistake here in terms of age. Let's see what else. There are some useless attributes. And as I mentioned, if the data is small like this, then removing attributes might not be a good idea because it might not reduce much in terms of complexity, unless the column is adding noise rather than information. So the attributes which are useless can be removed to improve the computational complexity as well. So can you figure out what column that could be removed? I know you get it right. The first ID here, of course, after we remove our redundancy, then this is a unique value for each and every instance. And unique value will not help our model. And that's why it will not add any value to the training model. So, all right, we understand this is, in this case, each value is different from the other, right? It's unique values. But if you look at this column, what's the problem with this column? Which is the status, whether the person is married or not. For this particular data set, all the cases are just not married. So in this case, I don't have to keep this column because it doesn't add any value. In fact, it may add noise. Why? Because for a case such as this and a case just right above it here, they are supposed to be different. Why? Because the class is different. So the 0 has to be in a 0 class and 1 in 1 class. But the more you have attributes that they don't distinguish between the two and treat everything as the same, that in fact will affect the classification accuracy. And it's better if you remove a column with only one value. All right, anything else? Of course, there are more pre-processing techniques that could be helpful to be applied here, such as, for example, this data is clearly unbalanced. By unbalanced, we mean one class is more dominant than the other class. And this is a typical problem in data science or in machine learning. So, in class 1, we have only 3 instances, but we have 7 in class 0. So 70% of the instance actually belong to class 0. And this may affect the classification ability of your model as well. Of course, we need to find a way. If we can balance these classes, that would be excellent for our learning process. We're going to deal with this in the future, and we can see how we can handle it when we do our practical part based on this lecture. There are other pre-processing techniques which could be very helpful when we normalize the data. Because when we normalize the data or scaling the data, we're making the data points generalized, close to each other, make the learning even more efficient. This is another pre-processing technique can be applied here, especially when you have things like the one we mentioned here. All right? So, now we understood what kind of pre-processing work we do in our data. When we perform this pre-processing, then our data will look better and then we'll be ready for the learning step. But if you look here at, for example, the $sign, do you think we should remove them? In some cases, it depends on what kind of learning system you use. But since you define what the column all about, you don't have to keep it. For example, if you are using Excel sheet, you are reading from Excel sheet or CSV file, then the $sign is understandable to affect the value. But if you remove it, since you know we are talking about car value here or house value or income, then it won't make any difference. It's better if you keep it away. All right, now, the pre-processing let's assume that is done. Of course, if you look at the data, we did not really make that changes. But let's assume that we have the data set ready now. So our next step in the process is actually to input your data set to a classification model in order to start learning from it. But somebody may ask a question. The idea here is we understand that from this data set, which is the training data set here, you are going to create or apply a classification technique. Why? Because if I have a new case, the new case can be compared to the model, then the model will advise this class will be 0 or 1. That's what we are looking for. All right. That's perfect. But let's understand when we say model, what's the model look like? If we look inside this model, what it is. There are many classifiers. And how the classification work in this case. So let's look at 2 dimensions here. In this case, let's assume only 2, we're picking only 2 dimensions or 2 columns from the data, the income and the car value, for example. The income and the car value. So if you take these 2, you can plot them in X and Y, Z, in X and Y axis, right? All right. So then we find that in this case, let's say this is just a hypothetical representation of the model. Then you may have, this is the first class and this is the second class. The class, let's say, of zeros and 1. Of course, this diagram doesn't really correspond to this data set because we have only 3 in one class and 7 in the other class. But here to illustrate how the model works. So now, if we plot both of them, then we have our points the way it is. Then in this case, we can easily separate between the 2 classes by having here linear separation. In advanced topic later on, we can look at techniques like support vector machine, for example, classifier, which try to learn to maximize the margin between the 2 classes here. We're going to talk about this in the future. But as I mentioned, this kind of lecture is meant for somebody starting with 0 knowledge, and then we're going to grow together until we go to advanced level. So if I have 2 dimensions and I plot this from my training data, now I have the new case, which is the case 3577609. Let's say this. When I take the same X and Y axis, which is the income and the car value, this is the income here and the car value, then let's say I found the point light here. In this case, I'll know straight away this is going to belong to class the circle red, whether it's a 0 or 1 or whatever. So that means here this kind of new data point is belong to this class, not this class. If I have a new case fallen, let's say here, this will belong to this class, not that class. That's the basic idea. Of course, in this case, we have more than 2 dimensions, and that's the beauty of going from 2 dimensions to multi-dimensional. Because the separation cannot be, just linear. Or sometimes you may look at a class and you cannot have a linear separation. But if you have a 3 dimensions, maybe you can find that separation between one class and others. So the higher the dimensions are, sometimes will give us more, better ways of classifying data. Okay, now let's have another example. It could be a neural network. These are your input here. Let's assume here we have only 4 for illustration purposes. Then you have your hidden layers. We're going to talk about this in the future. And this is the class. So basically, you have weights will be assigned to each and every line here, and then we're going to learn whether this will contribute more to 1 or 0. We're going to talk in details on this. We're not going to introduce the topic right now. Or it could be a decision tree. So if you look into this is another representation of a model. I'm sure most of you heard of decision tree. So look at this example here. If we take occupation as a root here, then it has several variables. But you notice that whenever we have the variable manager, we always have a decision as class 1. And this here, we call them nodes. These are links, and these are the leaf node, which is the class. So if you look at our data here, see, whenever the occupation is manager, the class is always 1. And this is a kind of a patterns which is very important for us to make decisions. So if somebody comes to you, and for example, in this case, a novel case, this is a manager, for sure this class will be 1. Even if I don't look even in the rest of the attributes. That will give me a huge hint on a manager. Usually, yes, it doesn't mean managers making accidents all the time, but according to my training data, whenever the occupation is manager, is the case is always leads to accident or previous car crash. So, but when we look at blue collars, for example, then we cannot see that. You see, blue collars could be 1, blue collars could be 0. So we cannot say when the occupation is blue collars, that means which police and military. It doesn't mean straight away the person was in accident or not. This is not an indication here. In case of manager, 100% of our cases leads to previous accidents. Blue collar, not necessary. But if you look at blue collars, and then you go on car types, whenever the car is a van, they always have previous accidents. Not like other type of cars. So this kind of patterns will help me to, straight away jump into decision, right? And the model is just a collection of this kind of evidence and patterns for better classification. And the model could also be just represented as rules, as you can see here. If occupation is manager, the claim flag is always 1, right? Or it could be something like this. If occupation is manager and the car use is commercial, then the claim will be, the flag will be 1, or the class will be 1 in this case. Okay, so this is how our models, this is a quick overview on how the model works, on how it looks like from inside. Alright, now we understood what's the model all about. So again we said, from our historical data here, we can create a model to be used for future or novel data, right? So we can make easy decision here based on the model developed from our history, from the data we have. So, but how can we evaluate our model? How can we say this is an accurate model to be used? There's many ways of doing this. The simple way is to split your data into training data and testing data set. So in this case, I can train the data, I can train the model using only my training data set, the one highlighted in red here. This is the one will be used for as input for the classifier. So what's the purpose of the testing data set? This is to address the generalization issue. The best way to do it is to test the model. And in this case, as we mentioned, we have already know the label. So when I train the data on the red samples here or instance, then when I try with the green ones, which is the testing samples here, the model will advise me on what the class will be. And based on that, I can see, is the model predicted these classes correctly or not? That's very important. Then I can use it. Let's say I got the 99% accuracy or 90% accuracy. Then we could use it to predict novel classes like the one you can see right here. So you can simply calculate the accuracy by looking on something we call it true positive, true negative, false positive, and false negative. Or the accuracy is simply how many detected correctly versus the total, right? What's the true positive, true negative, false positive, and false negative? Let's see. Let's assume that you have 100 samples, and this is the actual class. So your model predicted these classes this way. You can straight away see there are some, classes not detected correctly, like the one highlighted in red. And also the one here in purple. You can see here, this is not also detected correctly because it's supposed to be negative. So here the true positive is, if it's originally positive and detected positive, this is a true positive. And if it's negative, predicted negative, this is a true negative. And that's what we are looking for, is to have more of the true positive or true negatives. But we have here a negative value which is supposed to be positive, so it's a false negative here. This is not a true negative, because if it's a true negative, it will be here. So we have here two false negatives, and we have here one false positive as well, because this is not a true positive, this is a false positive. But if you think of it, why are we looking into this? What about accuracy? Is not enough? Of course not. Why? Look at this typical case. And if I want to calculate the accuracy, what the accuracy would be here? Of course, let's even make it more like the detected classes, all of them are negative. Imagine this is all negative. So in this case, I'm getting 95% accuracy. It's very high accuracy, right? But none of the positive class is detected. And this result is deceiving here. Because in some cases you have classes, we talk about unbalanced data, but you can have a typical example like this. This could be a rare disease, or a success in operation, or dealing with disease, or medical surgery, or anything like that. Rare cases. And it's very important for me to detect the positive class here. So by detecting nothing, just putting all negative, I'm getting 95%, and that's not accurate. In this case, I'm getting 97%, but also it does not reflect how powerful the model is, because 2 out of 5 of the positive class are detected wrongly. And that's why we can have different measures such as recall and precision. And if you see here recall, we are again taking the true positives, which is the true ones here, plus the true positive divided by the true positive plus the false negative. So that means basically I'm looking at this class here for the recall. And similarly for the precision. In this case, we're taking the false positive in consideration, not just the false negative. So both of them will give me a better view on the two sides of the story. And then we can combine both, in which we call as F measure, which equal to 2 multiplied by the precision multiplied by the recall divided by precision plus the recall. In fact, was not intended to have formulas in this initial lecture, but at least this is very understandable when you look at these formulas here. So this leads us to which we call as the confusion matrix, and this is very important concept. Remember when we say if it's positive, detected positive, we call it true positive, right? And if the actual class is positive and detected negative, this is a false negative. Negative detected negative is true negative. Negative detected positive is false positive, and so forth. So the confusion matrix is the best way to evaluate our model. But in some cases, we notice that the data is too small. Because remember, we said we can split it into training and testing. In some cases, we're going to talk about this in the future, which in the case we have training, testing, and also validation data set. And we'll learn later the validation is just to ensure that you don't fall in overfitting the data by each classifier has different parameters to set, and you don't want to adjust it to the level that you improve your training very well, and then when you test it on a testing data set, then you got horrible performance. We're going to talk about that in future lectures. Now, if we have if our data is too small and would like to do the same thing, we can try something we call it 10-fold cross-validation or k-fold cross-validation. In most of the cases, data scientists use 10-fold cross-validation. And in this case, the data we have, we can split into 10 pieces. And we can take one piece as testing and the other 9 as training. And this process is repeated. The next step will take this as testing, remaining as training, followed by this as testing, and the rest as training. This is a better way to justify that you're not in favor of taking some testing data set for your data set to look good, or for your model to be more accurate. Because each and every example sometimes fails in the testing data set and sometimes in the training data set. So we can calculate the average of this process and we can have better evaluation of our model. So, and again, a confusion matrix could be used here in order to calculate what's the accuracy, recall, precision, and F-score.